So, hello everyone. Thank you for the very nice organization for today. It was amazing. So, my name is Ali Ismail Fawaz. So, I'm a lecturer at Université de Haute-Alsace in Mulhouse. And I do my research in the Erimas Institute. So, unfortunately, my colleague Germain Forestier was not able to come today. So, it will just be me. So, I will be presenting today aeon. So before talking about aeon in details and what we do in aeon, given that it's about time series, so I thought I will just give a small introduction about what is time series and time series machine learning specifically. So time series is any type of data that can be traced through time, so a single variable or multiple variable where we can trace its values, how it's changing through time. And so there's an ordering mechanism. So the difference between time series and tabular data is this ordering mechanism. And we can find multiple features in a time series. There's multiple ways of defining how a time series is changing. We can find some local dependencies between small segments. We can find global dependencies between multiple segments and all that. So there's a lot of type of ordering when we come and we say time series. So we call it time series, but not everyone actually agrees that we should call it time series. A lot of people try to call it data series. Why? Because the ordering is not always based on time. Sometimes it's based on position, sometimes it's based on frequency. So we use generally the term time series because for the past 30 years it was just common knowledge to say time series, but it's not always about time. So time series machine learning, there's a spectrum, a huge spectrum of different tasks that we can apply on time series. So the different tasks that we can see, for example, the classification, the most common one, try to classify time series in different classes, try to predict the class, finding patterns in each time series. There's its complement, which is extrinsic regression. Well, it's also called regression, but just to differentiate it to forecasting, where we try to predict a continuous variable that is associated to the time series. There's clustering that Guillaume mentioned, try to cluster the time series into similar groups. There's prototyping generation that also Guillaume mentioned, where we try to find a prototype, a representative that is very similar to the real data, and sometimes try to generate new ones, not only find a representative. There's forecasting, the most common one. Even if you don't know about time series, at least you know about the term forecasting. We try to predict the future part of the time series. And there is, of course, anomaly detection, where we try to find anomalies, uncommon behavior in a single time series. So, of course, there's a lot of different tasks, but I can only fit 6 in a single slide. So there's segmentation, there's similarity search, there's a lot of different tasks in time series machine learning. We try to cover all of them in research, but it's in aeon, sorry. So I will go into deeper how we get all of these in aeon. So, but before, I'd like to mention a bit of history about also the team, because it's not only me, it's a huge team that we got engaged in aeon on multiple time steps, let's say, on the last 3 years, because it's a very new project, let's say. It's only 2.5 years old, let's say, almost. So it's now it's a huge team. It started on a very small scale with some colleagues in the UK. So Tony Bagnall, Matthew Middlehurst, Chris Holder. So now in the University of Southampton. So there's us, me and Germain, University of Alsace. We have colleagues from Microsoft, from Germany, from Spain, from India as well. We're almost now all over the world. We still have no one from the US, however. So this is a plan for us in the future. So I'm gonna tell you a bit how we got all together. And small thing I wanted to mention. So other than today, we try always to stay interacted with the community, either research or industry, through tutorials or demos or anything. So with ECML, with KDD, with sometimes French conferences, EGC, if you're familiar with EGC. So we try always to stay interacted with the community, to show and engage with people, to tell them that open source is important. So it all started in 2019. from Tony's team in the UK with a project grant part of the Alan Turing Institute. And then Tony got a 3 years grant for research and development through software open source, which actually helped the foundation of aeon. In the early 2023, the branding of aeon started. Before it was not branded as aeon. The project was not officially has started yet, was not at the scale that it is right now. And in 2024 is where the big scale happened. We started doing tutorials, we started collaborating with other people, bringing other core developers into the team. So if I zoomed in between 2019 and 2024, so in 2022, we started shifting not only from classification and going into other tasks. So at the beginning, it was only for classification. Why? Because Tony's team was mainly doing research in classification. But then started to shift, and every time there was a new person doing a PhD or a postdoc on a specific task in time series machine learning, they got into the project, started to collaborate what they're doing during their PhD. So it started, for example, with regression, with David. Then I got into aeon because of deep learning, because my thesis was about deep learning for time series. And segmentation as well, anomaly detection, similarity search. So all these people were working at some point in their research or in their industrial work about a specific task on time series. And when they saw aeon, they saw that, hey, well, aeon is missing segmentation. What if I can come and contribute for this part? So this is how actually we grow, and we became like almost 12 core developers, I think now. So in 2025, so more recently, we started 2025 with aeon 1.0, where we actually removed all the old legacy code on forecasting. And we started a new module on forecasting that we started with Alex. So he was doing also his PhD in forecasting, so he mainly took part on leading this part. We started also a new module because there was a new PhD student that got integrated into aeon about everything related to imbalanced classification tasks. So this was not actually covered in aeon. We started doing Google Summer of Codes. So the last 2 years through NumFocus, we proposed projects of Google Summer of Codes. So we had interns online, mostly from India and China for the past 2 years. So we propose a new model that needs to be developed. We bring interns from Google Summer of Code, they get paid, and for 6 months, they work with us on developing such model. And more recently, well, in September, we were all in CML. We did a demo there. So we're trying every year to stay integrated and engage with the community, doing tutorials and all that with other people. So Jessica Lynn, Jeff Webb, even if they are not core developers in aeon, they are also collaborators, so they still integrate and engage with our work. And well, today, and more recently in October, we got into P16. So thank you, Selma, for this part. And Gael is not here, but I think he was the one that he was the one that mentioned it to Germain, I think. So so it was really great to get into P16. It was amazing, and today we are here. So I will now talk about deeper into the package. I will not go in a lot of details. There's a lot of stuff to talk, so in 15 minutes it's a bit difficult. So I will give you just small stuff. So I think you're very familiar with this very beautiful chart, because we took it from Gael's sklearn chart. So we did a similar one for aeon. So if you come to aeon, if you don't have temporal data, well, you should probably not use aeon. So if you have temporal data, you come in, and we have this huge chart to show you what you should do. So if you have, if you're trying to predict a target or a label, is it a categorical label? If yes, you go to classification. If it's not labeled, but you want to predict a label, go into clustering. If it's labeled, but it's continuous, go to regression. So it's similar to how sklearn presents its flowchart. So I'm showing you here I didn't notice it will be just that bad with the black background, but so here I'm showing you the base structure of aeon. So all of our estimators inherit and are based on the base estimator from a scalar. So all of the package is based on a scalar. We start with the base estimator from a scalar, we create our own base estimator, base aeon estimator, and then all of the estimators inherit from this one. So what you see in blue and orange, to differentiate between both, it's base collection estimators and base series estimators. So why do we differentiate between both? Because not every task and not every estimator works in the same way. Some of them train and predict on a collection of time series, such as classification and regression. However, in anomaly detection and forecasting, it's not the case. In forecasting especially, we are given a long time series, and we try to work on this long time series. We don't have a collection. So we call this series estimators. So this is why we differentiate between the two. It was much easier to differentiate the both because they don't have the same mechanism during training and prediction. So this is the differentiation between collection and series estimators. So I'm showing you here a chart about how the structure in aeon for each module. So here I'm showing the example of classification. Why? Because again, it's the most populated one, because almost all of us are actually, we have a background of classification research and time series, so that's why it's the most populated one. So the structure follows what happens in the state of the art. So we try really to structure aeon the same way as researchers structure their own work. So in classification, in the state of the art, it's differentiated into 8 different sections. So we have deep learning that I will mention now. We have shapelet-based that Guillaume mentioned, distance-based, so where we try to find distances between the time series like DTW and try to find the nearest neighbor between this. So this is a distance-based classifiers. We have feature-based where we try to find statistical features. So we structured these modules the same way that we find the state of the art in research, how they structure their own work. So deep learning is alone, interval-based is alone, feature-based alone. So this resumes a paper that did a benchmark on all classification tasks on time series, done by Tony as well. So now I will talk about the deep learning side. So, well, for one reason is because I work on deep learning, and the other reason is because I got into aeon because of deep learning. So during my PhD, Tony wanted someone to work on deep learning in aeon because we wanted to have a unique specialty in aeon that is not very common now, which is add deep learning into any task in the single package. So not for a specific task. So when we started on deep learning, we started only with classification. Now we are actually covering a lot of models. We have classification, we have clustering, we have forecasting, regression, and self-supervised. So we started with classification. We have 10 different models in classification. Some of them are convolution-based, some of them are self-attention-based, some of them are recurrent-based. And we started with clustering with the first Google Summer of Code in 2024. So the goal is, instead of doing clustering with machine learning techniques, we try to learn with a deep learning model how to cluster the time series data. With regression, it was much simpler because it's almost the same models as the classification. It's just that downstream task changes a bit. With forecasting, this is what we tried to start this year with aeon 1.0, with the Google Summer of Code of 2025. So trying to implement deep learning models for time series forecasting. And we have a new kickoff of everything related to self-supervised. So when I say self-supervised, it includes a presentation learning, and it will include foundation model. It will include anything that is unsupervised learning with deep learning models. So we try to learn a representation space of our time series data. But one unique thing about aeon is that we separated the downstream task estimator with its backbone network. So this is why you're seeing here networks with 20 models. We thought that if we create a deep learning model for classification, however, someone wants to use this backbone model but for something different than classification, but they still want the same backbone. So we wanted to add this into aeon. So the networks model includes all of the neural networks. So there is no training, there is nothing, there is just the implementation of the neural network, how every layer is connected between each other. So we use Keras actually to do this with TensorFlow backend. In this case, we give the ability to the user to just take the backbone network and do whatever they want in downstream task. So we wanted to add this feature to not obligate the user to use a specific task. So when I say deep learning for classification, so here I'm giving you an example of a very simple model. So the fully convolution network, just made of 3 different convolution layers. So each convolution layer has multiple convolution filters, one-dimensional convolution filters. Try to learn what are the parameters of these filters in order to, at the end, classify the time series. So this is for classification. For regression, it will be the similar, just that the downstream task will be to predict a single value. So this is for classification. This is one example, one of the 10 models that exist in aeon. For clustering, for example, one common technique that was done in the state of the art, which we include in aeon, is the autoencoding technique. So we train an autoencoder to learn a concrete and coherent representation in the latent space here in order to reconstruct in the prediction the time series that was given in the input. So we take then the representation space and we fix it and we train on top of it an sklearn estimator for clustering. So this is where sklearn comes into place. So we train, so the first step is to train this deep learning model. We can also use a pre-trained one and skip this step. And then we use a simple sklearn machine learning clustering model. When I say simple, it means that we assume that there is no longer temporal axis, so it's no longer a time series, it's now a feature-based, and we use it to learn a clustering model on top of it. So there's also time series averaging, so prototyping. So instead of just taking the average time series, we can also use deep learning to find such average. So the same technique, we learn an autoencoder model to find a representation space. So here I simplified it to have 2 dimensions in the representation space, but of course it can be much higher. And the prediction part to find a new representation, a new representative, a new prototype is to take multiple points in this latent space, find the average in this latent space, because we will assume that it is no longer temporal, it could be Euclidean, and then take this point, give it to the decoder, and now we have a new time series that is representative. So this technique is what is done in the state of the art for deep learning on time series averaging, and this is what we're trying now to add as a feature into aeon. So in terms of classification, these are all the models that exist in the state of the art. So here I'm showing you the results of performance with trade-off with complexity and efficiency of these models in terms of flops and inference, the size of the model in terms of number of trainable parameters, and the average performance over more than 100 datasets in the UCR, in the state of the art. So all these models are now into aeon, so you can use them to train on your own new data. You can also load the results of what you're seeing here on this figure through aeon as well. So if you also want the results to compare to a new model that you are proposing, you can load the results through aeon, and now you have a full benchmark comparison. You can see this figure on a website that actually we did, which is not related to aeon, but we're trying to link it to aeon to load the results automatically. So we can see the details of all the architectures that are into aeon with the original article that proposed the model, and interact to see the data sets, the results, and all this. So what we're trying to do now is integrate aeon into this website, try to load the results automatically in order, if we add in the future new data sets, we will also have the results added every time. So aeon has a roadmap now. So this year, the roadmap was about forecasting. So there's 2 axes. There's the machine learning and statistical forecasting, so statistical models, machine learning like setar, setar tree, and all that. And we also have the deep learning part for forecasting. So until now, we have TCN, temporal convolution network, if you're familiar with it, and deep AR, which is one of the two old but also famous forecasters in deep learning. We're trying now to integrate new ones like NBeats and all the new models that exist in the state of the art. At the same time, we're starting with self-supervised. We want to add more models into self-supervised because there's a huge state of the art in research about self-supervised, and they are used in multiple tasks, either if it's foundation model or semi-supervised learning or clustering, all that. Our goal, two things. So reproducible research. So this is a huge important part, and this is one of the reasons that actually motivated me to get into aeon. Because during your PhD, you stumble on a paper, you want to use it, compare to your model, you find that the code is not reusable, or the code doesn't exist, or if it exists, you cannot run anything different than their experiments. So it's a very huge, annoying thing during your PhD to stumble upon. So this is one thing that could help actually the research, is using aeon to create reproducible research. So if you end up, you create a model, get it into aeon, show that you can reproduce your research with 5 lines of code, and people will start using and seeing your work, and it will help with the visibility of your research work. And the other part is development of very optimized code, easy for deployment. So not just put the code into aeon, it should be structured, it should be optimized. The implementation should be very optimal. So for example, if we're doing DTW, we should implement DTW in a very efficient way, because if we implement it with naive Python, it's super slow. So the code should be easy to use. It should be structured well, so that if someone comes to contribute or reuse the code, it should be clear, it should be documented, and optimal in terms of time of execution. So these are our two important goals. And of course, go into full open source, not semi-open source. So thank you for your time. I think I took a lot, but yeah, thank you.